Hello, welcome. Let's try to solve another Leetcode problem. 1649. Create sorted array through instructions. So we are having such kind of instructions. So if the number of elements currently in nums that are strictly less than instructions I. Yeah, and there's another instruction, the number of elements currently in nums that are strictly greater than nums I. Yeah, let's just use an example, try to understand what is the meaning. So for example, we have nums like 1, 2, 3, and 5. So let me put it here. 1, 2, 3, and 5. So the cost of insertion is the minimum of the two operations. Yeah. So let's check the first operation. So for example, if we have a number of 1, 2, 3, 5. Now, if we were to insert a number, maybe 4. Yeah, so we're gonna calculate the cost. So before we insert this number, we are going to check how many numbers that is strictly less than my current number 4. So 1, 2, 3, so there are 3 numbers. And we're also going to check how many numbers that are strictly greater than this number 4. So there are 1 number. But we're gonna choose the minimum of the two, 3 and 1. We're gonna choose 1. So 1 gonna add to our result, so result should plus 1, and we're going to use this result set it to be 0 to plus all the operations. So from the beginning, the array is going to be empty, and then we're going to add 1, and then we're going to add 5 and 6, etc. And for each of the operations, we are going to check how many numbers of elements currently in nums that are strictly less than or strictly greater than my current number. Yeah. So the very obvious idea is that in Python we can use a sorted list. So from the sorted containers we can import the sorted list. Basically, we just need to use a binary search to solve the problem. We can prepare how many numbers less than, it's going to be L, and how many numbers greater than, it's going to be R. As you can see, we just use bisect left and bisect right to solve the problem. Yeah, but I don't think this is a good solution. Although it works, but this should be a hard problem. A hard problem should be used a better way to solve it. Yeah, basically, as you can see, this is solved the problem. But we used a lot of things, a lot of libraries. We used the sorted list, and we used the sorted list bisect left or bisect right. Yeah, basically we used the libraries to solve the problem. But normally we should solve it by using the binary index tree or a segment tree. I think that should be a better solution to solve it. So the idea is going to be the same. Yeah. Now, first of all, we need to check what is the length of the instructions and what is the number. Is it a contiguous binary index tree, or is it discrete? It means the numbers can be really big. As you can see, the maximum number is 10 to the power of 5. I mean, inside of the instructions I. Inside of the instructions array, the maximum number is 10 to the power of 5, and the minimum is 1. Yeah, so this means we can use the binary index tree directly, because our binary index tree is just starting from index starting. This is a binary index tree. It is starting from index 1 to n minus 1. Yeah, let's say just starting from 1 to n minus 1, it is still okay. So yeah, we have a dummy index 0, but that will not take part into the calculation. So the calculation will be just starting from 1 to n minus 1 if the length of the array is n. Yeah, because our biggest number is 10 to the power of 5, and this means we can use a contiguous binary index array. Yeah, so if we have this kind of binary index array, and we're going to use the index to start, we're going to use index as the instructions for each of the numbers. So for example, we have an array of like 1, 2, 3, 5. Yeah, so for each of the operations from the beginning, we have the index like 0, 1, 2, 3. Yeah. So if we are going to put 1 inside our insert 1 inside of the array, but before insert we can check how many numbers that is smaller than 1. So this is the index 1. We can check that is 0, and how many numbers that is greater than 1. And we can also check, so from index 2, it is also 0, so it is a 0. And then we're gonna insert number 2, but before insert, but after insert this 1, we're gonna add 1 to our current number. So for example here, it's gonna be added to 1. So before we insert the next number, it's gonna be number 2. Before we insert this number, we're gonna check how many numbers that is less than 2, there's only 1. And how many numbers that is greater than 2, so that is a 0. So we're gonna choose the minimum of them, so it's gonna be 0. So the operations are gonna be the same. We just need to prepare a binary index tree. Actually, it is an array, and then we're gonna put all the numbers inside for each of the operations. We just need to check, because inside there's the sum method. We can use the sum and add. So for the add method, we can add a number. Actually, we can add an index to the array. And for the sum, we can use its index. The sum is from index 1 to our current index, maybe x, maybe I. We can check the result. So if we use binary index tree, normally this problem can be solved easily. We don't need to consider about the index too much, because the binary index tree, while we are checking the index, it may be easier. It's not like the binary search, we have to check the index carefully. But for binary index tree, if we design it like that, normally for checking the index, it should be easier. Now let's just get started for this solution. So let's just prepare a binary index tree. I'm gonna use bait as a binary index tree. So this is a class. I'm gonna define the function. So for the init, I'm gonna prepare a variable n. So self.tree should be equal to 0 from the beginning times n. And for each of the operations, I'm gonna put the numbers inside. And I need a self.n should be equal to length of self.tree. This is just the initialization. Now I need to have a low bit, and it's gonna be bit I. I just need to return this low bit. It's gonna be I and minus I. Also, I need to have the end method. So it's gonna be, I need to add a value to index I. So this value is gonna be k. I need to add k to index I. So for the add operation, if we were to add to an index, normally it's gonna be the value gonna become smaller and smaller because we use the low bit operation. So for example, if we needed to use add 7, it's gonna be add 7 to 6, because 1 1 1 we're gonna flip the low bit, it's gonna be 6 we're gonna flip the low bit, and it's gonna be 4 flip the low bit, it's gonna be 0. So for the add operation, the number gonna become smaller and smaller. So we needed to check the index I. If this I is more than 0, we're gonna add it. So self.tree with our current index I should add to k, and as it is a low bit operation, we're gonna use a minus the self.low bit with this bit I. Now we need to finish our last method. It's gonna be the sum, as I defined. Sum is just index I. It means we're gonna sum up from index 1 to index I. We're gonna sum up all those numbers inside the self.tree array from index 1 to index I. For the sum operation, actually it's gonna be increasing. It's gonna be plus I plus the low bit. So for example, we're gonna sum to at index 4. It is index 1 0 0. So we're gonna add the low bit. So the low bit is still 1 0 0. So it's gonna become 1 0 0 0, and it's gonna become 8, and it's gonna become 16. It's gonna be like this. So this is for the let me check. Did I do something wrong? I think I did something wrong. For the let me just Uh, for the end, yeah, I did something wrong. For the sum, it's gonna be become smaller and smaller. Yeah, this is why we need to understand it. Otherwise, it's gonna be wrong. Yeah, let me check. So, for the AND operation, we need to check this I should be less than self dot n. For the add operation, it's gonna be become smaller and smaller. But yeah, I did it right, I think. Let me just yeah, finish the sum function. So the sum gonna be add gonna become smaller and smaller. Sum gonna be yeah, let me just finish it. If this while I more than less than self dot n, I'm gonna need to have a result. Yeah, so for the sum operation, if I would to sum up to 7, if I use the sum up to 7, it's gonna be 7, 6, and 4. So it's gonna become smaller, and I think add operation gonna become smaller and smaller. For the sum operator, this is a binary index tree. Yeah, sometimes it's gonna become yeah, if I use the sum operation, if I use the sum 7, it's gonna be 7, 6, and 4. So this gonna be the sum. But if I use add operation, I'm gonna add a 4, then to 8, and then to 16. So we have to understand it correctly, otherwise we did it wrong. Yeah, so just yeah, I'm sorry for that. I think for the sum operation, it's gonna be sum 7, 6, and 4. It's gonna become smaller and smaller. For the add operation, it's gonna be bigger and bigger. Yeah, so this means I need to change a little bit. Yeah, let me just change it from here. Yeah, let me just finish the add operation. Let me just finish the sum operation first. So I'm gonna return while this is more than 0. So result should plus equal to self dot tree I, and this I should minus the low bit. So this is gonna be the sum operation. So for the add operation, so I need to check it should be less than the boundary. It's gonna be self dot n. If it is less than the boundary, self dot tree with I should plus equal to self dot should plus equal to this number k, and then I'm gonna update it. I'm gonna update it to a bigger value, so I should plus equal to the low bit with I. Yeah, so this is gonna be the add operation. So if we were to add a number, so for example, if we were to add a number 4, it is 100. We're gonna first add it to the position of index 4, and then we're gonna add it to index 8. Yeah. So for example, first of all, we're gonna add at index 4, and then we're gonna add it at index 8, and then 16. So this is the add operation. We cannot add it at one place. So if you are familiar with the binary tree representation, it's gonna become bigger and bigger. So this is gonna be the add operation, and here gonna be the sum operation. Yeah. So if we finish the template now, well, we can start. Actually, here should be easier than other problems because this one is really easy to recognize. We're going to use T maybe to represent the binary index tree. So the T is going to be the binary index tree, and inside I'm gonna give a variable of n. So this n gonna be the 10 to the power of 5 plus 1. Because our result for the maximum number it is 10 to the power of 5. So I'm gonna have a length of the array more than that, so 10 to the power of 5 plus 1, because I will not use the index 0. So here, for the binary index tree, I will give this variable n, and we're gonna use it to solve the problem. Now we're gonna prepare some variables, result and mod. Result gonna be 0, and mod gonna be 10 to the power of 9 plus 7. So this is given in the description. Now we can check the instructions one by one. So for I in instructions, basically we need to find the left and the right. So how many numbers at the left side and how many numbers at the right side. Currently I will give a 0, 0. I just want to finish the main structure, and the result would equal to result plus the minimum of this L and R, and with a mod. And finally we need to return the result, but we didn't finish the sum and add method. So for this L and R, basically we need to use the sum method to get the result. But after that we need to use the add method. So T needed to add our current value. So it is this value I. So it is the instructions. It is this number. And for the L and R, and we can also calculate it easily. So it's gonna be T dot. It's gonna be T dot n minus 1, because n is 10 to the power of 5. So for our binary index tree, it's gonna be T dot with sum of n minus 1. It's gonna be 10 to the power of 5. Not plus 1, otherwise it will go out of the boundary. So this is R. So it means from the right side it's going to be minus my T dot sum. So with the current number, so it is this I integer. And for the left side, it's going to be T dot sum with I minus 1, because I need to check how many numbers that is less than this number I. Maybe I is not so good. Let's just use X. It is just a number. Maybe X is better. Let's just use this X. So this is going to be the entire code. Now let me just run it to check if it works. I'm missing a variable. It's going to be at this index with a number of 1. Because we're gonna count it as 1. I forgot the low bit, self.low bit. Now as you can see it works. Basically for writing the template and writing the code, it may produce a lot of bugs. We have to check it carefully. Now let me submit it to check if it works. Now as you can see, it works, and the time complexity is n log n, and this n is 10 to the power of 5. And because we are preparing this binary index tree, and this n is dependent on the maximum number of instructions, it is 10 to the power of 5. Another number n is the length of the instructions array. It is also 10 to the power of 5. That is why we're going to use the n log n to represent the time complexity. And the space complexity is O(n). That is for preparing the binary index tree array for this array. Thank you for watching. See you next time.